Okay, so we've seen non-convexity, we've seen over-parameterization, like we made our network wide to try to get around some of the challenges of non-convexity, and that was pretty cool, but still things are pretty slow, don't you think? And this is one attempt for us to maybe work on a less precise version of gradient descent and make it go fast. So this is what we're doing now. We saw that we need to do a full gradient, right? The cost of a full gradient is very high, and we don't like that. So we're going to work on those mini batches. And this is the summary of this section. Let's look at it. All right. So this was a gradient descent step on empirical risk. Okay, we're doing empirical risk minimization. And in order to get a full gradient, we're using, or full batch gradient as we say, we're using the whole training set, which comprises n examples, right? For MNIST, this is 60,000 examples. So for big networks, this can become problematic because even computing the gradient for one example can be relatively costly, right? One of those gradients for I equals 1, for example, right? This can be costly. And then we need to do all of this n times just to, like thousands or millions of times, just to do one step of the algorithm. So do we really need to see all those examples to do one single step? And the answer is actually no, thankfully. And the answer is mini batches, okay? We are going to do mini batches or stochastic gradient descent, depending on who you ask, these terminologies are used. And the algorithm is at the bottom of our screen, essentially, where we go from the top right, where we do a full batch gradient, n points. Instead, we are averaging at the bottom over a smaller number of examples, a smaller number of gradients, right? So the set BT is a subset of the training set, and it can have a size that's 10, that's 100, that's 1,000. We will discuss the size soon. Some people will call this method stochastic gradient descent when the size of BT is just 1. Okay? Other people will use the term stochastic gradient descent even for larger batch sizes. So beware of this discrepancy in the terminology. Okay? So, but what is the deal here? We're not taking the actual gradient. Are we even minimizing the right thing? Right? Because the way we started this whole discussion, we need the gradient of the objective to minimize the objective. Now we're not using the gradient of the objective, but we have this estimate, right? So at the bottom, this gradient, you can think of it as a noisy estimate of the full gradient at the top. And it works very well, okay? This is the summary. It's much cheaper to compute, and it works very well. So this is the discussion. So the gradient updates we get are worse, meaning they're less accurate. They don't always point in the direction of steepest descent, but on average they do. That's a good property they have. But we can do many iterations. In the same amount of time it would take us to do one full gradient step. And that leads to huge speed-ups in practice. It's impressive. Okay, we're not guaranteed to find the exact minimum that we would find with full batch gradient descent, but that's okay. Things still work well. And I should also remind you, we're already working on a surrogate objective. Our original objective was the true risk, okay? But instead we're using a surrogate objective, which is the empirical risk. So it's important to keep that in mind, because if we're a little bit off in optimizing the empirical risk, it's probably okay because we're already using a surrogate objective. Okay, and it turns out in practice things work quite well. So we want those mini batches to be representative of the true data distribution if we were to look at the whole data set, right? So mini batches are often selected at random, let's say with replacement or even without replacement from the full training set. Or we can select them in order after we have shuffled the training set. Okay, we do one shuffle and then we go in order. The statistics are a little bit different, but still work out generally well. Okay, so this is mini batching. How should we choose the mini batch size? Here's a rule of thumb. Okay, first the extremes. If we have a too small batch size, okay, our optimization method will bounce around a lot because the gradients are too noisy, right? We're estimating the full gradient using a small number of examples. So it's bound to point in all sorts of directions and have significant discrepancies, right? So that can lead to slow convergence, okay? That's not optimal to use a batch size that's too small. On the other hand, we have an engineering or a practical constraint, which is the memory that's available to us. If we're using a GPU, it has a limited amount of memory, and there's only so much we can grow our batch size before we hit an out-of-memory exception, right? So the rule of thumb for now is try to go for a large batch size and make it fit into your GPU. So modern day GPUs for modern day problems, if you max out the memory, you're probably fine. And of course, you can always, for each different problem, you can play with it and see the relative performance. But a good rule of thumb is max out your GPU memory and go with that. Okay? Okay.